speaker will be Michael Koepf and Technion, one of our organizers, and he'll be talking on continuum model of epithelial spread.
Here you go. So today I want to talk about a continuum approach to the modeling of epithelial tissue dynamics. This is work that I've done together with Len Pisman at the Technion. This work has been funded by HFSP. And I put another institution logo down here, which is the logo of the École Normale Supérieure. And as you notice, I put this in brackets because I'm actually just about to start working there in 2 months. So this means I will set up my small shop there as a junior research chair. This means that all the work today basically has a future perspective, at least for the next couple of years. And that's why I'm particularly looking forward for lively discussions throughout the week and hope for lots of feedback from the audience. So let me begin by introducing the motivation behind our mathematical model. So what we are interested in is wound healing. And when I say wound healing, I'm not talking about the messy and complicated process that sets in when you, for example, cut your finger, but I'm looking at a simpler and more idealized situation where a monolayer of cells recovers from damage. You can consider, for example, this simple enough experiment where a monolayer of cells has been grown on a substrate. Then part of this monolayer is scratched away and the experimentalists observe how the remaining tissue recovers from this damage. But of course, in reality, this process is by far not as clean and clear as one would think by looking at these pictures here, because it is practically impossible to scratch away parts of the monolayer without leaving lots of rubbish behind. So you will have remnants of the extracellular matrix, you will have cell debris, and most importantly, you will damage cells at the edge of the wound. And this makes it extremely difficult to decide what the control mechanisms and the driving forces in the wound healing dynamics actually are. Because these injured cells here, they will emit an injury signal which will influence the dynamics of the remaining tissue. But many people argue that this signal is actually only of secondary importance and that the most important fact is simply that we have here the sudden appearance of open space that can now be easily invaded by the remaining cells. And to isolate this effect, one has to come up with an even cleaner, a more idealized wound, which can be obtained by the process of unconstraining. The unconstraining works like this. We again grow a monolayer of tissue on a substrate. But now we have also on the same substrate a barrier made of some suitable material which can be removed without leaving anything behind and without damaging the cells here at this edge. So we have no injury signal in this situation. And this experiment has been carried out, for example, in the group of Pascal Silbazin in Paris. And they grow cell monolayers in such stripe-formed stencils, which can then be peeled off. And what they observe afterwards can be seen in this photography here. So you can see we have very strong undulations in the boundary lines of these stripes. And if we take a closer look here, we can see that we have actually very large protrusions, which are localized, strongly localized structures. You can see they are very heterogeneously distributed. You see on this side we have 3 very large ones. On this side we have maybe none, or maybe a very small one here. And another remarkable fact about these structures is that they actually appear on a time scale which is much faster than the time scale of proliferation. So this means these fingers do not grow out of the layer, but they actually result from a collective motion of many cells which work together to form such a finger structure here. So if we want to describe with a continuum model a phenomenon like this, then this picture basically defines the scope of our model. So we are interested in such deformations here of a tissue. Then of course we are interested in the tissue mechanics, interested in elasticity, interested in traction exerted on the substrate, in the stresses. And I've put here a picture from the group of Jeffrey Fredberg to show that these quantities actually can be measured quite accurately nowadays. They can also do time-resolved measurements like this. But the question that really gets me passionate about this topic is actually this question. So how does the collective behavior emerge here? So how does a large number of cells decide to behave collectively to form such a structure? And for this, obviously, we need at least these 2 ingredients here. Well, if a cell wants to behave collectively with its neighbors, it first of all needs to know what its neighbors are doing. This means there has to be some means of communication, which on the tissue level can be achieved, for example, by chemical signals or by a direct reaction to mechanical cues. And then, of course, the cells have to act according to this communication, which means they have to take some action, and what they actually do is they polarize and they start exerting active forces in some preferred direction. So the simplest continuum model, which has all these features here, would contain three quantities of interest. We would have here a two-dimensional vector field X, which gives us the position of each point within the tissue. This is basically the information about the shape of the tissue. Then we have the concentration of a chemical species, which serves as a chemical signal in the tissue. So we consider here only the simple case where there's only one single chemical signal around. And then finally we have another 2D vector field P, which gives us the local polarization at each point in the tissue. And of course, these three quantities are strongly interrelated, because if there are active forces along the polarization direction, these active forces will lead to deformations of the tissue. As a reaction to this deformation, the cells will emit a chemical signal, and this chemical signal will again in turn influence the polarization. So I will take the next few slides to describe how these three fields actually evolve with time. So first of all, the deformation. So deformation is of course controlled by elasticity, and what we do is we consider the tissue monolayer as a weakly nonlinear elastic material, a thin layer whose thickness might vary with space, but whose dynamics are essentially two-dimensional. So in order to quantify the deformations, we always consider the current deformed state and compare it back to a reference undeformed state. So we define a mapping between these two states. From this mapping, we can calculate the so-called deformation gradient tensor, from which, again, we can calculate the strain tensor. And from this, we finally can set up the elastic free energy of the system, from which we can straightforwardly obtain the stress tensor. So,
do you assume that this layer is attached to substrate rigidly, or it can slide?
It can slide with friction. Yes. Yes. So, as I said, we are essentially two-dimensional, but then we need, of course, to have some relation between the thickness of the layer and the two-dimensional dynamics. We make here a simple assumption that the material is in 3 dimensions incompressible, which means that the height is given by the initial height over the Jacobian of the in-plane deformation, which basically means if we compress the layer locally, it becomes thicker. If we stretch it out, it becomes thinner locally. Okay, from the stress, we can calculate forces by taking the divergence. And since the dynamics of such a layer on a substrate is dominated by friction, we can write down such an overdamped dynamical equation. And so far, of course, here, this material is just purely passive, so it's just an elastic material. But we now add active force here in this form. So you see this force is proportional to the polarization vector with some proportionality constant Q, which gives you the strength of this active force. The polarization itself also obeys an overdamped equation of motion with the suitable free energy functional. So this functional actually is not as complicated as it looks. You just have to take 2 messages from this slide. First of all, we have an interaction between the concentration field, that's the chemical signal, and the polarization, in the way that gradients of the concentration field induce the polarization. The second thing is that in absence of this chemical signal, the dynamics is governed by these terms, which damp the polarization. This means that the material will remain unpolarized without the chemical signal. The signal itself is governed by an equation like this, so it diffuses throughout the tissue. It decays linearly with time, and this the most important thing is it depends on the strain. So what we have is we have here a strain-dependent source or sink term, and the dependence, the easiest way to model a dependence on the strain is to make a dependence simply on local expansion and compression. So we quantify the strain by the in-plane deformation Jacobian here. and introduce some sensitivity parameter beta. So here's an overview over this model. So the three equations our model is made up of, and I just explained how deformation induces the chemical signal. I explained before that the polarization is induced by gradients of the chemical signal, and finally the polarization gives rise to an active force which enters the mechanical equation. So in order to understand this, the properties of this model better, we can now look at the linear stability of the quiescent state. The quiescent state would be just the simple situation where we have the undeformed tissue with the completely unpolarized state and with no chemical signal around. And if we linearize around this state, we can exploit the fact that we can express the deformation and the polarization field by its divergency. So we can write down these three coupled linear PDE here. And you can see that apart from these two friction coefficients, eta and gamma, we actually have only three parameters left, Q, alpha, and beta. So just to remind you, alpha is the damping constant in the equation for the polarization field. Q is the strength of the active force, and beta is the sensitivity of the signal generation on strain. It turns out that for the question whether or not the quiescent state is stable, the individual values of beta and Q are actually not important, but only their product, beta times Q. And so we can draw this two-dimensional parameter plot, beta Q against alpha, where we have three qualitatively different regions. First of all, the boring stable case, where perturbations would just decay to zero, but we also have these two different instabilities. We have an oscillatory instability for negative beta Q and a stationary instability for positive beta Q. So what does the sign of beta Q actually mean? So it's reasonable to set Q to a positive value. This just means that the force is in the direction of polarization. And then positive beta Q just means that the chemical signal is generated upon expansion of the layer, whereas negative beta Q would mean that the chemical signal is emitted upon compression of the monolayer. So let's have a look at these two instabilities. Start with the oscillatory instability. I'll try to show you movies here. Yes, so what you can see here is in color the concentration field. The arrows indicate the polarization field, and you can see that we have domains oscillating between high and low levels of C, and the polarization field rotates basically to keep aligned with the gradients of C. In the other case, the case of the stationary instability, we don't have oscillations, but we nevertheless have interesting time evolution, because in this case we have domains which form and then grow with time. So again, it's the same color as for concentration, arrows for the polarization field. So you see we have domains which grow with time, smaller domains merge. So it's kind of a coarsening dynamics that goes on here. This means the characteristic length scale of the structure increases with in the course of time. This can be visualized, for example, in a diagram like this, where we have the length scale against the time. This has an interesting implication, because if you imagine this dynamics to go on not simply in a plane, but on some closed surface, let's say a sphere, then you basically start with a completely symmetric situation where you just have a sphere, which you perturb randomly. Then on the sphere, domains pop up. These domains start to merge until in the end, as you will see, only two domains remain. And so one domain with high concentration, one domain with low concentration. And this means you have here a very natural mechanism to establish starting from a completely symmetric situation, to establish a situation of permanent polarity. And I think this, although it's a rather abstract model, I think it's an interesting mechanism, because I think in biology, in many systems, particularly in early development, the establishment of polarity is like one of the first important steps. And here it comes out very, very naturally. Okay, to bring us back from this, as I said, rather abstract model to the beginning, so to the case of wound healing. let's consider a situation like this. And of course, since we have here this stripes with a wound edge, we now have to consider boundaries. So we basically have to make a system like we had it before with a free boundary. For the mechanical equation, it means that we have stress-free boundaries. We further assume that the chemical signal is confined to the tissue itself, so we have no flux through the free boundary. And for the polarization field, we assume that the directional derivative of P here at the interface vanishes. And the interface itself, or the free boundary, has another very interesting implication. Namely, it has we have to take into account wetting and spreading. And this has actually nothing to do with the material being made up of cells or being biological material. It's simply a physical consequence of different interfacial energies between substrate cells and monolayer, cells and surrounding medium, and substrate and surrounding medium. And just like you would do it for a liquid drop on a substrate, you can calculate the spreading coefficients from the three different interfacial energies. And the sign of the spreading coefficient basically tells you whether the tissue wants to cover as much of the substrate as possible or whether it wants to contract as much as possible. This gives, for our model, an additional force normal to the free boundary. And we assume here only the case where the materials are wetting, so where the tissue wants to cover the substrate. Okay, we further to really describe the actual experimental findings in this wound healing, we have to make a few modifications of our first model. So first of all, we have, as I just mentioned, the wetting force as an additional new player in the system here. Then we have here a different type of active force now. So to remind you, before we had active forces just proportional to the polarization field, but actually from experiments it seems to be more reasonable for this particular system to have a coupling like C times P. So actually the strength of the active force depends on the concentration of the chemical signal. And we have a more direct way of for the polarization to influence itself. So what does it? Just let me mention. This is actually what we are doing here is actually a continuum version of a cell-based model, which has been investigated by Marco Salm and Len Pisman earlier. So this is just for comparison. And this is what our equations look like. So the system is the structure of these equations is actually very much like it was in the first model I presented. So we still have the equation for the chemical signal such a strain-dependent source term. We have included here a Heaviside function, which is due to the fact that from experiments they say that actually compression remains neutral, so it does nothing to the signal, but just expansion leads to the generation of new signal. Then we have, as I mentioned, the wetting force appearing here, and the modified active force with C times P. So the final additional ingredient that we have in the case of wound healing is that we include proliferation. So what we do is that we select random sites throughout the whole course of time. We always select random sites where we locally let the tissue grow. And the problem is, when you have growth, you always have a kind of non-trivial problem with elasticity, because as I mentioned, we quantify deformation by comparing a current deformed state to an initial undeformed reference state. But if in the course of time the material has grown, then of course the initial reference state does not give us the undeformed state of the grown material. So this is actually shown or visualized in this picture here. And fortunately, there has been developed a very nice formalism to handle this. Actually, one can simply decompose the deformation gradient tensor into a part due to growth, quantified by a growth tensor, and a part which captures really the elastic deformation. It's denoted here as A. And then we can set up the elastic energy and the stress and everything just in terms of the elastic deformation here. That's exactly what we do. Okay, with this we are now in the position to make a numerical simulation. We try to mimic these experiments with the stripe-shaped stencils. What we actually do is we take a Y-periodic stripe here with an open or with a free boundary at the sides. And so let me try. Okay, and what you will see, it's again concentration is the colors, and polarization field will be the arrows that you can see soon. So what we see is we have close to the boundary the formation of localized active domains, which then start to build this type of protrusions, which look very much like this fingering behavior that we've seen in the stripes of Pascal Silbersan's experiments. So what's our hypothesis? What's going on here? So the point is, first of all, the material itself, it's in a linear, in this case it's linearly stable. So it needs to overcome a certain threshold in order to develop activity, in order to become unstable. And actually the random perturbation, which is always here due to the proliferation, is not enough to overcome this barrier. But at the boundary, where we have, in addition to that, this wetting force, which leads to a stretching of the material and to a generation of the signal, then together with these perturbations is actually enough to locally overcome this threshold, and so we have these localized structures. And I want just to mention that actually I think this is the right way to do it, because I think it has to be some sort of nonlinear instability, because as you have seen in the experimental pictures, these fingers are distributed heterogeneously. So there's not like one characteristic wavelength along which they appear as one would expect for the case of a linear instability. Okay, of course we can do this also for different geometries. It's basically the same. And one can then look at the velocity orientation within a finger as compared to the bulk. And not surprisingly, when one has seen the movies before, within the fingers we have very well-aligned velocities, whereas in the bulk we have practically random distribution, which is driven mainly by the random proliferation events. This matches very nicely the findings of Pascal Silbersan, who did the same statistics for the actual tissue. Finally, one can also look at the stress, how it evolves with time. So what is plotted here is the XX component of the stress tensor averaged along the y direction of the stripe for 4 consecutive points in time. And what you can see is that in the beginning we have only these 2 small peaks close to the wound edge. Then these peaks grow and actually travel inwards. Somehow you can imagine it like a wave coming from the outside in till they meet to this one peak curve. And this again matches very nicely experiments that have been done by Jeff Fredberg and Xavier Trepat. So they first published in 2009 a paper where they made where they showed only one measurement of sigma xx against the distance from the edge, and there they have basically this curve only with one maximum, which would correspond to this state. But they later, in 2012, published another paper where they were able to measure really the stress time resolved, and they actually observe like the same general behavior. They have this stress coming up at the boundary and then traveling inwards in form of something what they termed mechanical waves, and which matches the behavior we find here. So I think we are probably on a good way with this type of modeling here. This already brings me to my conclusions. So we have developed a continuum model for active tissue, which we describe as weakly nonlinear elastic material with our 3 main quantities x, p, and c, which we consider. Then we have seen that for even a simple set of feedback and interactions, we can obtain these 2 different types of instabilities, the stationary instability and oscillatory instability. We have seen how the coarsening, which is seen for the stationary instability, can provide a natural mechanism to establish permanent polarity on a sphere. or any closed surface. And we have then moved to the case of unconstrained spreading, where we have free boundaries, and we have seen that the model captures this strongly non-uniform fingering behavior. We've seen this global tug of war. This global tug of war is basically the state where the stress has this one maximum state. And we have seen this type of mechanical waves which travel from the wound edge inwards. So I thank again for funding the Human Frontier Science Program and you for your kind attention.
Simon, we open for questions.
At the very beginning you said
Yes.
that your slow process appears from much shorter time scale.
Yeah.
Could you repeat this, explain what is the connection with short time scales and what it is?
Okay, so it was just the picture with the fingers. And the idea is, the question is where do these fingers come from? And then you can look what the time scale is on which these fingers form, and you compare to the time scale that it would take the cells to proliferate enough to grow to such a structure. And then you can see that this happens much faster. And this tells you that actually the layer does not grow very much while he forms or while it forms the structures. So this means the structures really have to appear due to some collective motion and active forces which stretch out part of the tissue.
Is this much faster than self-oscillations you described later, or?
This is to the oscillations. That's I think I could not directly compare it because the one thing is with a slightly different model than the other, so it's difficult to compare.
Can you show again how you put the wetting force when fast or knee?
Okay. Yeah. So what we in the end do is that we have a force which is normal to the free boundary.
So you have a force normal to the free boundary.
Yes. So we'll see. I'm not sure if it's actually written. It's basically this one. Yeah. We have a wetting force normal to the boundary.
Can I ask another question?
Yes.
The question is about the fingers. Do they continue to grow very long? Because there are only small bumps in the pictures you show. And there's another question that goes with it. In fact, the experiments of Trepat and Silverzon don't say the same things. Trepat never has long fingers, never has long protrusions, and Silverzon always has them. Do you understand the difference? It's the same cells.
Yeah.
In my eye, it looks exactly the same experiment.
Yeah, so that's I don't know the difference, but I think it's a general problem that I think if you make experiments with biological materials.
No. Come on.
No, it doesn't mean
you have to pass these answers.
There has to be a real difference.
Yeah, no, right. I mean,
No, of course there has to be a real difference. I just mean that you cannot, from reading the paper, tell what this difference is. That's the problem. So I don't. Of course, there is a difference. I mean, it's science in the end. It's not what I claim. I just say that it's difficult to tell what the difference is, and I don't know it. And I think from just reading the papers, you cannot
so
tell.
they have the same substrate, for instance. I mean,
So the substrate is a little bit different.
there you go. I mean, the spreading force. I mean, your FIJ. I mean, if there's an instability and if they are factor 2,
It would be very important.
What happens to your fingers? Do they saturate to a long length?
So the problem is that if you would, this is actually beyond the capabilities of this simulation. So you would have to go further to use some more sophisticated simulation to go to really large deformations. So
Does it have to be large deformation, or could it flow because the tissue is viscoelastic?
actually, so here I again believe Pascal Silverzon, who says that this happens actually on scales where the viscosity does not play a big role. That's why we have here only elasticity. I think if you want to model it for like a very long state, you will also have to include viscosity at some point. But for the onset of these fingers, it's probably not important.
Carsten?
So,
So in your force balance equation, you add this term Q times
Yes.
P. Why do you call this an active force? This is just an external force, isn't it?
It's still an active force because it comes out of the polarization of the cells.
But then wouldn't
So-
you add it rather to the stress?
So I don't know. I mean, the point is, I imagine that we have some interaction with the substrate, which is not covered in our two-dimensional elasticity, which is covered by the stress we have, and this the active force then formally appears as an external force. That's right. It's an external force.
Is there a qualitative difference with the, for example, fingering that you observe when you pump a fluid into an unmissable fluid? You have two fluids and you pump one into the other, you get fingering.
Yes.
Which is, I mean, that's the external also force. One liquid, you pump it into the other, and you get something that is similar. And I wonder whether there is a qualitative difference, macroscopic one.
There's a question why it should be related, because I don't see really the
dynamics. You have a dynamics and you have fingering, and
Yes.
I wonder what makes this so special or biological with respect of the fingering that we know from fluids, for example.
I think it's a completely different mechanism that creates the fingers here. I mean,
The statistics regarding the fingering, the instabilities, the macroscopic pattern.
I'm not even sure. For example, this instability is a linear instability, or
That depends on kind of.
Last question, Shira. Shira.
You might get a term resembling what you are calling the active force if you introduced the conventional active stress and then integrated the equations over the vertical thickness, maybe.
But this is a monopole, it's not a dipole. So if you integrate over the whole thing, you get a net force that is acting on the system, and if it's just active...
No, but if you have a film and you have a piece of the stress bilinear in P, if the system is polarized, then if you take the divergence of that and integrate it over the vertical coordinate, you might get a term linear in P.
Isn't what you're writing just an active friction of the substrate?
it's actually
Okay, we need to close the discussion. If you have more questions, maybe you can.
So I just wanted to say that maybe the strength of cell-cell additions can impact if you see fingering or not.
the
So
strength of
if the cells don't adhere strongly to each other,
Mhm.
then it's more likely probably for it to finger.
Is it an experimental result, or
I'm just kind of.
all right? Okay.
Okay, I
guessing.
think we send the speaker again for extra talk.